In this lesson, we're going to look at another way we can use the ideal gas equation, which is the combined gas law. We're going to learn how to simplify the combined gas law for any values that are constant, and we're going to use the combined gas law to solve for any unknowns in a problem. To look at the combined gas law, we first need to start with the ideal gas law. The ideal gas law is intended when we have 3 of our 4 unknowns plus our ideal gas constant, and we can solve for the missing value. There's 1 pressure, 1 volume, 1 moles, and 1 temperature. However, there are times where we're looking at comparing 2 sets of conditions, and so we want to get to an equation that we can use to compare those conditions. To get to the combined gas law, we're first going to rearrange to solve for R. Remember that R is a constant. To better understand how we're going to make this arrangement and write the combined gas law, we're going to pause from the chemistry for a second and look at a math problem. If A times B equals 10 and C times D equals 10, then we know that A times B equals C times D. Because both of those expressions were equal to 10, therefore they must be equal to each other. Okay. Remember that R is a constant, so if 2 things are equal to R, then they must also be equal to each other. And we're going to use this to set up the combined gas law. The way we do this is by looking at 2 sets of conditions. Note that R equals PV over NT, and even if we change the conditions, that equality is still true. R still equals PV over NT. Therefore, if 2 values are equal to R, they must be equal to each other. We use the 1 and the 2 as subscripts to recognize which set of conditions we're talking about. So for example, on the left, we say these are conditions number 1. Sometimes you might hear this called the initial conditions. On the right, we have our second set of conditions. We call them number 2. Sometimes you'll hear these called the final conditions. The term on the left is equal to R. The term on the right is equal to R. Therefore, they must be equal to each other. And this is known as the combined gas law. We use PV equals nRT when we have 1 set of conditions, so 1 set of variables for PV, N, and T. We use the combined gas law when we have 2 sets of conditions. There's some type of initial setup and then a final after some change has occurred. So we might see 2 pressures or 2 volumes, and that's going to give you the clue of whether or not you're going to use the combined gas law because there are 2 volumes and 2 pressures, or there's 1 set of pressure, volume, temperature data, so we're going to use the ideal gas law. Let's look at an example using the combined gas law. A 5-liter sample of propane has a pressure of 2 atmospheres. What is the pressure if the volume is decreased to 3.5 liters at constant pressure? As I look through the problem, I see that I have 2 volumes and I have 2 mentions of pressure. One is known and one is unknown. Because I have 2 sets of conditions, some kind of initial state and some kind of final state, this tells me that I'm going to use the combined gas law to solve my problem. I'm going to first look at conditions 1, and I see that the volume is 5 liters and the pressure is 2.0 atmospheres. Next, I'm going to look for conditions 2, and my volume is 3.5 liters and the pressure is my unknown. That's what we're looking to find in the problem. So we're going to start with our combined gas law. P1V1 over M1T1 equals P2V2 over N2T2. The first thing I realize is that I have P and V data, but I have nothing about N or T, so I have no numbers to put in for those. However, the way we talk about N1 and N2, we see that N is a constant. It says a 5-liter sample of propane. It doesn't say about adding additional propane or removing propane, so we can assume that N is constant. So if N1 equals N2, these values can cancel out. Next, I look at the temperature, and I know that T1 is equal to T2 because the problem told me we were at constant temperature. Because T1 and T2 are the same, we can cancel them out as well. And what we're left with is an equation that has P1V1 equals P2V2. Now we can plug in the values into our equation, and we get our pressure times our volume equal to our unknown pressure times our volume. Now we can rearrange the equation and solve for P2, and we get 2.9 atmospheres. A sample of N2 gas has a pressure of 1.2 atmospheres at 25 degrees Celsius. What is the pressure when the temperature is increased to 75 degrees Celsius? As I look through the problem, I notice that I have two mentions of pressure. One is given and one is an unknown, and I'm given two temperatures. For my first conditions, I'm looking for my pressure, which is 1.25 atmospheres, and I also need my initial temperature, which is 25 degrees Celsius, and I have to convert that value to Kelvin, and I get 298 Kelvin. Now I need to look for my conditions number 2, and I see that the pressure is my unknown, and my final temperature is 75 degrees Celsius, which I need to convert to Kelvin and get 348 Kelvin. Now I can take the combined gas law, P1V1 over N1T1 equals P2V2 over N2T2, and I'm going to look at the variables that I'm not given any values for, the number of moles and the volume. In the problem, there is no mention of the volume, no initial or final value, no mention of change, or any increase or decrease. Since it's not mentioned, therefore we can assume that there's no change, and if volume 1 is equal to volume 2, then they can cancel out with one another because they're equal values. As in our previous example, our moles are given as a sample. There's no indication of increasing or decreasing the amount of our moles of our sample, so we know there's no change. So N1 is equal to N2, and those values can be canceled out. We're left with the simplified equation of P1 over T1 equals P2 over T2. We can plug in our values, and we get 1.25 atmospheres over 298 Kelvin equal to our pressure 2, which is our unknown, over 348 Kelvin. We multiply both sides by 348 and we get 435 over 298. We do our division and we get P2 is equal to 1.46 atmospheres.